goes on with recording. Two things that we have it. One is called as a long-term materials. Sorry, long-term material behavior. I was with the new keyboard.
The recording is not happening.
It will. It is going on. It's going on. Yeah. One we have it's a long-term material behavior, and the other actually that we have it is something called as a short-term material behavior. So two things that we have, one is a long-term material behavior and the other one is a short-term material behavior. Now in the long-term material behavior, actually, what it comes is like, it is going to come it as like undrained material properties. So when you just go for this, it is called it as an undrained material properties. And when you just go for this particular short-term material behavior, in the short-term material behavior, it is something like a, sorry, I'm writing wrong. Drained. Now this is like undrained A. Let's reduce this. You have it like undrained B, and the other model that you have it is like undrained C. But beyond these particular three, that we have a one more material, and that particular material we are going to call it as like non-porous. Okay, so when we have these particular material behaviors actually, so what we can able to see is like, so these are the material behavior properties that we can able to see. Long term is nothing but your drain. Short term material behaviors are like an undrained A, undrained B, undrained C, and there is a non-porous material sample. So when you are just trying to feed up this particular material properties, there is a one more important parameters that you need to remember. Those parameters are nothing but your strength and stiffness. So those parameters are nothing but your strength and stiffness. So if you just go for strength, this is your strength, and the other parameter that you are going to feed is nothing but your stiffness. So this is your strength and stiffness that you are going to feed it here. And now when you just go for your strength and this, actually this model says that actually this is an says it is actually an effective properties. So both strength and as well as this thing, both are like an effective material properties is what actually that we can able to see from this particular model. So this says that effective properties actually. So the strength and as well as the stiffness are like the effective properties. Here actually if you just come to this particular part, this is an undrained A. Here also this is also an effective material properties, because this is also an effective material properties that is going to come both. To see. Sorry, come on. this is not linking to this. Okay, so now actually if you see this one in the undrained A conditions also, actually it takes this particular effective properties only. Both the strength and stiffness are going to be an effective properties. But in addition to this, actually here, there is a one more thing that is going to come. And that particular thing is nothing but, if you just say, pore pressure will calculate above the groundwater level also. Pore pressure will calculate above the groundwater level actually. So you have to be very careful while using this particular things and all. So that means you are calculating an excess pore pressure conditions and all. Even if you see these particular things actually, if you just consider this one here, if you just consider this is an two properties, but this is only for strength actually. So this is an effective property only for the strength, and the followed with that actually this is like strained shear. This follows this undrained shear strength. So okay. The stiffness follows like this and the strength follows like this. Stiffness follows like this and as well as the strength follows like this. Maybe it would be like a little complicated after plotting this image, but try to remember this when you look into the arrows. It would be like more easy for you to remember this. So and when you just go for this an undrained Sika condition actually, both are like drained properties only. Both the strength and stiffness that you are feeding it, both the strength and stiffness would be like only the drained material properties that you are feeding it. Now I need to bring this one. Yeah, you can just follow this one. So this is where actually you can see this one. We have a long-term material behavior, short-term material behavior, and then as a non-porous material. If you take it as a long-term material behavior, so always we are going to call it as a drain material property. Or if you go for a short-term material behavior, we are going to call it as an undrained A, undrained B, and undrained C. And if you go for a long-term material behavior and it is a drain material behavior, and in the drain material behavior that you are feeding a properties as an effective properties, which you are feeding it is like both the strength and as well as the stiffness, you are feeding it as an effective properties. And if you are going it as an undrained A conditions actually, and if it is an effective properties only that you are feeding it, both the stiffness and strength you are feeding it in terms of like an effective properties only. But when you just look into this particular things and the effective properties, that is the pore pressure, you can say like this, yeah. In the effective properties, the pore pressures will be calculated above the groundwater level also. And in the undrained way, actually the effective properties will be feed for the stiffness and for the strength actually that we are going to feed this undrained shear strength. And if you see it is an undrained C, both the strength and stiffness parameters that we were feeding it as a drain material properties, which are like a non-effective material properties, you can see that. And for the non-porous anyways, that we know that it not possible to calculate, no possibility to calculate the go through it, because the water will never enter into this kind of material, so that it will never be an entering into this. So this is all clear, right? So what is an undrained behaviors, drained and undrained behaviors, when to choose a drain and when to choose an undrained gate conditions. That's all driven based upon your material inputs also. What kind of material inputs you have it, based upon that it is going to drive this. So I hope it is all clear. Do you have any doubts on this understanding for drained and undrained conditions? Okay, I'll take your silence as no, and then I'm moving on to the next topic here. So moving on, so we have just selected this particular soil material for the problem that we were discussing about it, which is having a circular footing and all. Yeah. Now I just created this particular thing, and I selected the water level also. And the water level I have just selected as a 2. Now I just need to create a material. While creating a material only, that we just end up with this. So now I would like to create a material that is like a sand, and the best is always like a mokolum. And here the behavior is like a drain behavior. If I'm selecting the drain behavior, then make sure that the properties that you are feeding, like the stiffness and strength properties that we are feeding, these two are like effective properties. And you have to provide a saturated and unsaturated weights like of the soil that you are selecting. And what is the material properties that we have been opted for this, that if you just like to see this. So if you just go for this, we have it in this attachment itself. So this is where actually, so I would like to ask a question, like anybody has tried it on the Sunday? Okay,
I tried that first one.
okay,
No, sir.
so it makes, okay, fine. Yes, sir, no.
Oh,
Okay.
Borolog I have created.
Okay,
Borolog.
fine. Yeah. The ones who has been done, do you feel it's comfortable, easy to use?
Yes, yes.
Okay.
Multiple Borolog I
Then,
have to create, and it's comfortable.
yeah, fine. Okay, fine. Now I'm just creating a material. So the material model is like a more column, saturated and unsaturated weights of 17 and 20, and the model here they are calling it as a drain conditions. So let me sign and naming it as lesson 1, and the saturated weight and unsaturated weights are given it as like 17 and 20. And the parameters I'm just going here. It's like an Young's modulus is like 13E3 kilonewton per meter square. 13E3 kilonewton per meter square, and the Poisson's ratio is something like 0.3. Okay. And the cohesion is like 1. I'll tell you that to the cohesion value, if it is not available, always try to feed it as like a unit value of 1. Why? I'll tell you that again when we have some examples for that too as well. So the friction angle is like 0, and the dilatancy angle is like friction angle is 30, and the dilatancy angle is like 0. This is the basic soil material properties that we were feeding it. Now we just got to know how to feed one particular material properties. Just give OK. If you have not done anything, then automatically it is going to throw you an error actually. Okay, so please be do that. And if you are a guy very much interested on your soil and you would like to perform multiple testings and all, which is not part of a Plaxis training of an advanced Plaxis, you can say this, but I can just show you some hint over there, so you can just practice it on your own, and then you can able to do that. And you just go for sand and just click on this particular soil testing. So majority of the companies will not have this particular license, but you can just go for this. And the soil testings in this actually, what type of a test that you wanted to, triaxial test or a cyclic testing or a odometer test results. So whatever the test that you wanted, you can just go there and keep all your material properties and run your simulations. And these are all the material properties that you are following it. And this is an initial cell pressure and the maximum strain that we are feeding it, and the number of steps, that is like 100 steps for this particular triaxial testing. Type of the testing is like a drained or an undrained conditions that you need to choose it. And compression is a direct compression or an extension also it is there that you need to select it. And the consolidation is like isotropic conditions or it's a KO procedures and all. So you have to choose this. and then make sure that you run this particular model. So based upon this particular model that you are going to get it like the failure cycles of this and the other diagrams, the strain rates of your things along to your stresses. So sigma 1 minus sigma 3 for deviations is what this is what it is going to get. This is your complete material behavior. So if you see this, if you have this particular information as per the triaxial testing, and this is where actually your part it is going to be failed. So you can just go and check like what is the maximum stress that you can able to feed for this particular soil material. Okay, so this is where actually based upon this you can able to go for your structures or like how much you need to strengthen this particular thing, those kind of informations that you can able to do it. But right now I'm not taking you too much onto this particular thing, but you can just do your trial and errors. Feel free to ask me for any kind of a materials. I'll provide you that particular materials and all. Okay, so that one particular option is there. So now it is a soil testing, just giving okay. Now you can just go and assign that particular soil. So now that particular soil will be assigned it over there. So just give okay, that's all fine. Now it is all good as per the diagram. If you just see this particular thing, let me close this. As per the diagram, if you just see this, the problem it says that actually I have like 2 meter, that is like circular means, so it's a 2 meter diameter actually, and then it is like a 4 meter depth and the footing everything I'm just going with. And as we all know that this is a circular footing, I'm selecting this as like an axis symmetric condition. So axis symmetry, that means about this particular y-axis the problem will rotate. So if I wanted to make it as a planar, I'm going to make only the half model of this, because this is an axis symmetric model. Only half model I need to do. That means about 2 meters of length, I would like to model only a 1 meter, and the 1 meter is going to be a reflection, because it's an axis symmetric conditions, because it's an axis symmetric condition. Okay, let me do one thing. I have this. I will just show you that for your better understanding. I will just show the complete image so that you will completely avoid. If that particular software is opening, I'll show you that. Yeah, it may take time to open that. So this is where actually, so I'm going to do only the half of the model for this. So that's where, this is where it is there. So the center axis. So from this is like 1 meter width. I can just go for my foundation. And in overall problem, if you see from this side to this side, or from here to here, what is the width? They have not given. What is the width? They have not given it anywhere. So as they have not given it anywhere, that you need to assume that one. So to assume that particular width, actually what will happen, you know, and why I need to assume that, and how much I need to assume that. So if you just go for this particular thing, and an axisymmetric problem, if you have a diameter, 3 to 5 times of the foundation diameter, that you have to consider this as a length. That means this is 5 meter, 2.5. So totally it is like 5 times. If I go, I'm just going around like 12.5 meters the distance that I'm just going with. So why I need to go for this? When there is a footing happened over here, and there is a lot of vibrations coming onto your soil, and there is a lot of settlements coming onto your soil. As the foundation is sitting it over here, now the vibration waves slowly it will start, and slowly it will reach us to some distance, and then it will disappear completely. So as per the dynamic laws, it says that actually, again, the quasi-Newton method says that when this kind of things are there, it's always better to study a 5 times max, or like a 3 times minimum. If your geometry is too large, if you feel, then 3 times minimum, or if your geometry is good enough to extend that 5 times to that. If you consider the geometry, then automatically this particular thing will really helps a lot. That is what actually the Newton Raphson it says that. So that is what I recorded it. So when you just go for this kind of this is killing. Yeah. When you just go for this particular foundation, so now this is where I have just fixed it is like 1 meter. But how on what basis the remaining thing and all it is considering is like, again, that is based upon the file, project properties. Yeah, that's good. This is open, so I'll tell you that access symmetry software, how it will understand it, I'll show you that. Jayashree, this is very, very important for you on your project. Maybe you can just also record this. And moreover, whatever the Cassine foundations that you have given me in the boards, those particular designs are also developed in this kind of software only. By just looking into the images, I can able to say that. Yeah. Okay. Yeah, moving on this. Now, model. If you see here, actually, it is telling that X minimum is this, X maximum. I have what is 2 meters, like half is like 1 meter, 5 times is like 5 into 1. So the maximum I can go up to like 5. And this is Y minimum is this, and Y maximum is like 4 meters is my soil thickness. I have it. I can just go it is like 4. Just give okay.
They're not visible, sir. Screen.
Is it same for all?
No, no.
Okay.
Visible.
Okay, so now actually this is 1 meter I'm going to occupy it. So 5 times of it like 5 meters. And this is like a 4 meters that I wanted to as a depth. So I can just go it is like 4 meters. Now if you see this, this is where like a 0, X minimum is 0, 0. You can see the coordinates at the bottom. Here the coordinates will come, okay? If you see this is like 0, 0. And if I move my cursor, this is like 5, 0. That is X is going for 5 meters. And now this is like 0, 0. And this is where like 0 and minus 4. The y coordinate says it's like minus 4. So it's not mean that are you given this particular boundary and later on I can't add beyond that. While creating a borehole, this is what is the soil layer. By default, it will create it. But in addition that if you wanted to go in a depth wise, you can add one more soil layer and you can able to do that as well. Yeah. Let me go to this. It's very long time for me to work on this, but let me try to show you that particular image once. So this is a plane actually that you are working. Maybe let's select that you are working on this particular plane, and then you are moving over here. And this is where like an axis symmetry with the foundations that you have it. Okay. Let's say that you have, this is your soil layer. You have, this is your soil layer. And over that you have 0, 0. Over that you have, this is your foundation. Yeah. Now actually in 2D that what you are doing it, this is how actually you are drawing this particular thing. But software, 2D software of Plaxis, how it will assume that it is an axis symmetric model, right? So it has to be assumed in such a way that okay, your software will assume that particular model in this direction. Your software will assume that in this particular way. So I don't know why it is not rotating, but you can just try to adjust this there. Okay, your software will try to understand your particular model in this particular way. Now you got an idea what is an axisymmetric model perfectly, and don't make any other understandings. Please stick on to the same understanding. This is an output. So maybe your axisymmetric model, you can just go there and you can just give it. This is your output, and to the output actually the input is something that you are doing it in Plaxis 2D is this. So in Plaxis 2D you are giving it like this, and the software is assuming it in this particular way. You got it? Yes, no, please.
Yes.
Okay. Don't do any mistakes on any, don't misunderstand yourself on any other thing essentially. So this is where an axisymmetric conditions actually. Now, if you just go for this and you have something like the front view. So this is what is actually your front view it looks. When I just cut only the half of the portion that you would be able to see that. And this is where actually your left side view, if you just wanted to see, this is where actually your left side view and all it will be. And top view, yeah, this is where actually you can able to see your top view. This is a one circle, dotted circle you can see, and this is a full circle you can see in your diagrams. Okay, I'm just closing this. Okay, so this is where that you have to remember this. The input is this and the output is going to come like this. That is what actually the Plaxis 2D will understand the things in that particular way. And now when I'm just trying to apply a load from here to here, then that means it is a circular load, entire load it is going to be applied over there. Okay, so now let's do that. So now I just finalized it everything. Now moving on to the structures. Now I was calling this particular thing as like a rigid foundation, right? So I was just calling this particular model as a rigid foundation. Now let me save this particular project. So I'm just saving this as a rigid foundation. Now this rigid foundations means directly there is a no footing. I'm going to apply the load directly onto the soil itself. So that's why I'll just go simply create a line load. If it is a line load, I'm just simply going create it, a line load, and starts from 0 and ends at like exactly 1 meter. And now what is the value of this particular line load? That we just need to feed this, right? So the value of this particular line load is something where we have it is like load value, how much they have given. Or they have given it as a displacement, so that you just need to check it. So in both the cases that we will try to solve the problem, and then we will try to achieve this particular things. And yeah, as Bharat asked one question, like it will automatically says that what is its limit. Yeah, that is also possible now. So I'm going to tell you that particular limit also. After what amount of a load actually the soil will get collapsed, that is also we can able to identify that particular things. So now they have created a soil, they have assigned the soil, everything, and this is where. But please be remember when you are just going through this particular material, whatever been highlighted like this. So read only that, it is really good enough for you. Now this is where actually they are creating it as like a prescribed displacement. They were creating it, not instead of a line load, they were just creating a prescribed displacement. So the prescribed displacements they were creating it, and the displacement is like 0.05. Okay, let's for the time being, just for the apple to apple comparison, we will just follow the same thing. So it's being a line displacement again from that particular point to this particular point, and the line displacement is something what we have seen it is like a uniform in the negative y directions minus 0.05 meters. This is the line displacements that we have seen it here. Okay, so where it is like a 0.05 meters that they are feeding up this particular value. Okay, now go to the mesh, and to the mesh actually just generate the meshes. As this is a small one, you can just go with the coarse mesh also. Just give okay, fine. And do you feel that you are applying a load over here, which we have already discussed all these things and all? Okay, go back to your classes and watch the videos. Click on this. If you would like to go for a coarseness factor, automatically 2.25 it has been selected. That's fine. So no need to change anything. Go to the flow conditions. I'm not going to change any water flow here. Just simply go to the stage construction. Now into the stage construction that we have spent time on why we are selecting it as a KO procedure, because I have a uniform surface of the soil over there. So that's why I'm just selecting it as a KO surface. If ununiform surface was there, then I'm going to select it as like gravity loading. Okay. So that's where like we are going to select it. So now it's only the KO procedure, stage construction, groundwater level only, and ignoring the temperatures, everything is fine. Now adding a new phase. In this particular new phase, I'm just naming it as like displacement. I'm applying it. So other things and all default, I'm leaving it. Default, I'm leaving it. Please be remember that here also the default, I'm leaving it. Just give OK. So the other things are also default, I'm leaving it. Now click on this particular displacement, and this is a line displacement. Please activate this particular line displacement. Okay, the line displacement, it has been activated. So if it is like a dynamic line displacement, then I need to activate this, but this is just a static loading right now we were doing it. So just a line displacement, you can activate it. Yeah. Now these two I'm done. So simply I'm just trying to solve this. It says that if you would like to plot any kind of a graphs that you have not selected any kind of a nodes is what actually it was showing that. Okay, let me ignore that particular things, and then I was just trying to solve this particular problem. Now you can see these numbers actually, how the sigma m stage is going. The moment it reaches to a 1, the problem is solved. And I'm just considering sigma m weight as a 1 because 100% density of what I'm giving it, I'm just considering that. And the stiffness is slowly coming down. That means soil is slowly getting collapsed. Okay, once the soil is getting gained a position, and again it will just start collapsing for that particular thing. And if you see that for the displacement I have given, what is the amount of a force that I'm applying is like, this is 74 kilonewtons, that is where. So it is just trying to adjust this particular part. It is 75 kilonewtons, 80. And as per the Newton Raphson, it is solving around like 240 steps and all. Maximum steps I can go up to like 1000 steps, and maximum iterations I can go up to like 60. But then now each step will have a multiple iterations. That is where actually it is going on. Okay, so now it's a time like it's all like about reaching 0.99, and then it will reach us to 1. The problem will end. Yeah. Now you have a successful solutions. But suppose if a problem reaches to up to like a 0.8, and then if it failed, it's meaning that 80% of the load it is capable of taking it. That means out of 0.05 displacement, 80% of the 0.05 displacement, that is like 0.04 meters of a displacement it could able to bear. After that it was failing. That's the meaning actually. So again, that we have discussed in detail about that. So please go through that particular links also. But if you have any doubts, stop me and then ask me the question. Yeah. Now, once if it is done, just you're not in front of the machine, but the problem got solved. Now you just wanted to know at like what force actually the solution has completed successfully. So just double click on this particular displacement. Now if you double click on this displacement and slowly come down, here you have something called as 79.70 kilonewtons. This is where actually the reached values. So the force in a y direction, for that the given displacement is like 79.70 displacements. Kilonewtons of a load, that was, it is really applying this much amount of a load actually, it was applying this. Okay, so the sigma reached proportions is something like 0.9993 is where actually the accurate answer that we could able to capture it. Okay, so just give okay. Now I would like to plot this particular view calculations. So click on this, there is a button called as a view calculations. So now if you click on this particular view calculations, then it will take you to the Plaxis viewer. So you can able to see all your results over here. Okay. Now, actually, it will show you results for which phase that you are doing the results actually. That if you want to see this is scaled up to like 5 times. So the image that whatever it is displayed here, it is actually having a scaling and it was scaled up to like 5 times of that. Okay. But the maximum displacement it happened is like 0.05 is what I have given it. But what happened is like 0.05987. And that happened at element 300 and at node 349. Okay, if you want, you know how to switch on this element numbers and all these things, so you can able to go and check that particular things and all. Suppose now I would like to see the deformations. You have an option directly called as in control 2. Put control and 2, so then automatically it will show you that particular image in contour wise. So in the contours and all. Now you can see this. This is where like I have all the phases listed over there. When I just click on the initial phase and it is an empty soil where I don't have any displacements. And if I just go on to the phase 1 where I have a displacement over there. Okay, where I have a displacement over there. Now another phase it is coming. How actually the displacement it is displaying it also, I can just tell you that particular part as well. Okay, if you want, you can see it is like a phase level displacement, or if you want, you can see the total displacement also. Okay, now if you would like to see the stresses of that, go and you just put like pore pressures actually, and P active pore pressures that if you would like to see it, and this is an active pressure, but the pore pressure is calculated at the initial phase that if you want to see, you can see this one. Okay, so this is how actually you can able to see your pore pressures. And if you don't want to show these particular boundary conditions and all, you can just go fix it as you can off, so that you will get a better animations or pictures. Now you can able to see this one. Now the stresses, principal effective stresses that if you would like to see that, now you can able to see the sigma 1, sigma 2, sigma 3 based upon your Mohr Coulomb that you would like to calculate. You can able to check for all these things. So this is what actually the stresses for sigma 3 that if you want, and the sigma 1 that if you want, and the sigma 2 that if you want. Effective stresses this was. But if you would like to see the total stresses, principal total stresses also, that it is possible over there. Okay, so this is in y directions and z directions and x directions. So all the 3 directions it's going to show that, because though you are solving in 2D, Plaxis is going to assume that it is in 3 directions, and then it will show you all the informations about this. Okay, and if you would like to see in terms of like a contour lines, you can just click on this, or if you want to go for a shadings, you can see this, or if you would like to go for any principal directions, that you can able to go for this one. So this principal directions will help you that in which directions actually the soil is getting moved or something. The load it is coming. So this side of the soil it is trying to move in this particular direction because of the load it is coming. Okay, so this is actually the soil movement and all that is happening here also. You can able to see this one. Okay, now this is where actually that is good, where you could able to see this one, and you can also able to plot the curves also actually. So you can just click on this particular curve and click on new, so that it will allow you to plot the curves actually. So And now first I just like to do for this, whether you wanted to do as a project wise or you wanted to do on a particular node wise. If you would like to select it as a node wise, while running the solver itself that you need to select it. Okay, now the x-axis, it is like multiplier. So the multiplier is always like what you want. The displacement that you have given it is on the x-axis that you want, and the force it is on the y-axis. So now you select this sigma m stage as your displacement, because the amount of the load that you are feeding it, it is taking in terms of like 100%, that is value to 1. So and then it is going to spread this. So now it is sigma m stage is here, and the force in y directions that I would like to calculate it. So just give OK, and this is how actually you can able to see this particular things. Now you can see a mark over here. This is where like actually you can able to see a peak is going around like a 82 kilonewtons. There you have reached it is like 79 or 74. If you just go back here, and if you just look into the reached conditions, it is 79.7. You can consider this as an 80. Okay, and when you just go for this, the round mark actually it was showing is like 82.11. 82 kilonewtons is actually the right value, but after that again your solution is getting converged and more getting stabilized it, and that's where actually at the end you can able to see 79.73 kilonewtons of load. But actually here, as this is an axis symmetric problem, this particular thing is showing in terms of like a radians. So you have to convert that into a multiply this 2.5. You have to multiply this particular value with the 2.5, then you are going to get the right values over there. Yeah. So what is that explanation? It is given it over here. Once you have done it, all this particular things, they are going with a medium mesh, and we can able to see the mesh, the initial phases, everything that you are done. So it's all clear for you. And now we were just simply activating that particular things and all, moving on, activating that particular load, and they were just checking up this particular problem, this complete thing that we have discussed it in detail. And moving on, when you just go for the results, and this is how actually the results and all it looks and all. Yeah, they have just checked up only this particular part. But if I just would like to convert this particular thing, again actually what they were doing is like they were doing up with the flexible footing. Actually the flexible footing also, I'll tell you that. Okay, so they will create one particular plate element, and they can able to see the shear force and bending momentum diagrams onto that. So we were just going to cover this. I will just come back to the results over here. If you just yeah, this is what actually the plot actually they have done it actually. So here we were just seeing of the sigma m stage on y-axis, and onto the x-axis they were just going with like the load displacement curve for this thing. As you wish. Okay, axis wise and all, as however you would like to plot it, you can able to plot that. So no issues. And now if you just go here, this is where like they were selecting onto the x-axis u, the displacement, onto the y-axis they were selecting it as a sigma m stage. Okay, and now if you see this, 33 kilonewtons or something, because it's in the radians. If you'd like to convert this particular radians, yeah, this is where actually you can able to see this. So a sign like 188 kilonewton per meter square is what actually, but actually what we got is something around, you can roughly remember that it is like an 80 kilonewton per radians that we got. But actually that we were feeding in terms of like an 188 kilonewton per meter square if I want to apply the same load. So to the vertical component of the load on this. So it is nothing but how many is this? 188 kilonewtons into pi into 1 meter square is giving me like 900 kilonewtons of load. That is what actually that I need to apply for this. So as you already got the load, so maybe you can just put it as by 2 pi. So then you are going to get this particular things. So let's say you have something like 80, and then 80 divided by okay, 2 pi right, 2 into 3.14, 2 into 1.34, 80 divided by 2.68 will gives you around like some 28.85. That is actually the 30 kilonewton per meter square is the thing that you are just trying to apply it on this, and then you can able to see this particular displacements. So if you just go for this 30 kilonewton per meter, that if you apply it, then actually the displacement is something around like 0.05 meters. If it is like 188, the displacement might be a different value. So the displacement is coming around like 0.05. Okay. Yeah, that conversion I will tell you that. Okay. That conversion I will concentrate you into the coming class, but please be aware about this, the process of how we are doing it and how we were just able to plot this particular images. And whenever you want it, you can also close this. Now, if you just wanted to do this, just do a trial. Okay. And now going back to the structures here, going back to the structures, and now I would like to apply a line load. Now onto the same model, I just applied a line load. As I just changed something onto the structures, it's always recommended to redo the mesh. And done. Going to the stage construction. Now initial phase. From the initial phase, I will activate this particular phase 1, and I will click on this particular line load. And it is a line load that I need to activate it. And the line load, you just make sure that it is around, let's say that 16, yeah, 188 kilonewton per meter. This is what actually that we were just trying to activate it. 188 kilonewton per meter. That is kilonewton per meter square is a load that we were just trying to activate it. And now this is the displacements that we were doing. Yeah. Now let's try to solve this particular problem. I'm not selecting any particular point for the curves actually. Let's see this, how it is. So now this is the initial condition with only displacement, and again the initial conditions with line load. Okay, now the line load problem is solving it. Now see this, Fy is like simply 0. And if I just go for that particular same amount of load, it is getting failed. Yeah. Now the load advancement failures. And if I just look into this, it is nowhere. Just because of some other conditions, it is getting failed. Okay, let me do. Oh, okay. It's uplift force actually. I'm just trying to apply it. No, it is a negative force that I need to apply. Okay. It's a negative force that I need to apply it. Now this is the one, right? So I alone can solve only that particular problem. I can see that again it was failing it. That's good fun. So the soil body seems to be a collapse. Please inspect the output results, accuracy conditions not reached into your last step and all. So if you see that previously to this, the errors value also it is quite different actually. So let's take a pause here and then we will be working on this particular error. I'm going to solve how we can, what is the reasons that we are going to get this particular error, and how we can able to address this particular errors that we can see it in our coming classes. I
Can
will
you tell
take
me
it.
again if you don't mind?
Mhm.
Where do you get that manual?